So I'll just briefly go through the discussion which I made in the end of the last class, okay, where I was discussing about binary codes, okay. Online guys, can somebody please respond whether you're getting my audio properly or not? Online guys?
It's clear.
Yes, sir.
Yes,
Clear.
sir, clear.
Yeah. So in the last class, we were talking about the various binary codes using which you can represent information. Okay, we have seen what was so in the last class, let us wait for a few minutes. So I can allow everybody to start the discussion. Let us wait for 2 more minutes, then we'll start the discussion. So there are different ways using which you can represent information whenever you are talking about digital system design. So you have seen some of the different methods using which you can represent numbers. Basically, whenever you say you are designing a system, you are basically using it for processing some information. And whenever I say I'm processing some information to us, you are operating with digital systems is nothing but numerical quantities. Okay. So basically, you should know what are the various ways using which you can represent numbers. Okay. So we have seen there are different ways of representing numbers. So these are referred to as binary codes. Okay. So we can represent numbers using different types of binary codes. Okay. As an example, in the last class we have seen how can you represent this quantity called 10. Okay. So one way of representing this quantity is in representing in binary. So how do you represent this in binary? I can write 10 as 1010. So this is how you represent 10 in binary. All of you agree? Okay. So this is how you represent number 10 in binary. You can also use one more binary representation where what I will do is wherever, so I have a quantity called 10. So what I do, I'll count from zeroth place, first, second, third, fourth, fifth, sixth, seventh, eighth. This is my 10th place, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is my 10th place. I put a 1 here. Okay, indicating that the value which is given is 10. So there is one another form of representation. So both are binary codes. This is a binary code for me. This is a binary code for me. Even this also is a binary code for me. So I can have different binary codes. I can have different binary codes. So it is how you actually, based on the context, you should decide which form of representation you want to use. Okay, depending on the context of the application which you are designing the circuit for, you should identify which format you want to use for representation of that number. Okay, so I can have different binary code. So do you agree? This is also a binary code for me. Do you agree? All of you agree? This is also a binary code for me. Do you agree or not? Am I using any number which is more than one here? No. So in a binary system, there are only two numbers. Can be either 0 or 1, right? So am I using 0 or 1 here only? So I'm using only 0 or 1. So this is also a binary representation. This is also a binary representation. So this is one type of binary representation. This is another type of binary representation. So like that, any number can be represented using different formats of binary representation. So these are the alternate ways of representing 10 there. Okay, I can use this representation in some contexts. I can use this representation in some contexts. So which is suited for you? It is your decision based on the application which you are designing the circuit for. Okay, so like that I can have different types of binary codes. So I can have different types of binary codes. So I can have different types of binary codes. Other binary codes which you already know is BCD. So what is BCD? Anybody? The expansion of BCD is binary coded decimal. So BCD has how many digits? Using BCD representation, I can represent numbers between 0 to 9. So all the numbers between 0 to 9, I can represent them using a BCD code. So BCD code is normal binary code only. Okay. So 0 is represented as 4 zeros. 1 is represented as 3 zeros followed by 1. Right. 2 is represented as 0 0 1 0. 3 is represented as 0 0 1 1. 4 is represented as 0 1 0 0. Sorry, is it correct? 4 9. Next 5 is represented as 0 1 0 1. 6 is represented as 0 1 1 0. 7 is represented as 0 1 1. And finally 8 1 followed by 3 zeros. 9 then 10. Is there a code like this for 10? No. Why? We're talking about BCD. BCD stands for binary coded decimal. Decimal means I have numbers from 0 to 9 only. So I cannot represent 10 using 4 bits. So what is the alternate way? How do you represent 10 in BCD? Represent each digit of the number separately. So how do you represent 10? How do you represent 10 in BCD format? How do you represent 10 in BCD format? I am writing it here. How do you represent 10 in BCD? So first one you represent separately and 0 you represent separately. So this will be 0, 1, then 4 zeros. This is the BCD representation of 10. So after understanding how do you represent numbers in BCD, you have understood how do you do BCD arithmetic also. So what is that thing you have to do? Whenever the result of the operation is more than 1010, whenever the result of a particular operation is more than 1010, to obtain the result in a proper format, proper BCD format, what you have to do? Based on the previous class discussion, what you have to do? Add binary 6 to it. So we have seen an example, right? I don't know how many of you remember or not. So let us, I'll just go through. Say for example, I am doing some BCD arithmetic like this. So where I'm adding numbers like this, 184, 576. I add these two numbers, 184, 576. I am doing BCD arithmetic, 184 plus 576. What is the result you get? What is the result you get, anybody? What is the result you get, man? Do it here. Tell me the answer here. Online guys, you can also tell me. 0 here, carry 1. What is the value you get here? Huh? 6 here, carry 1. What is the result you get? 760. So the answer you expect is 760. But when you are doing in the BCD, how do you do? Each digit you have to represent in BCD. Okay. So this one I'll represent it as this. 8 you represent it as this. Next 4 you represent it as 0, 1, 0, 0. To this you have to add 576. So 576 means 5 you have to represent. So this will be 101. 7, 0 followed by 111. 6, 0, 110. This is the BCD representation of 576. Now you are adding these two numbers. Okay, so you are adding these two numbers. Let me draw the straight line.
Sir,
Yes.
sir, few members are in the lobby, sir.
Few members are in the lobby. Ask them to join by time, man. There are so many, 9 members. So the answer you expect here is 760. Here it is 0101. Here it is 0 followed by 111. Okay, so we are adding these two digits there, these two numbers there. So what is the answer you expect? So we are adding binary 0, 1, 0, carry 1. This comes here. This will be any carry from here? No, right? 1, 1, 1, 1. Any carry from here? No. Here it will be 0, carry 1, 0. So this is fine for me. This is fine for me. What is the answer you expect? You expect 760 as the answer, but did you get 760 here? No. So to get the answer in the familiar BCD form, what you have to do is whenever the result of the operation is more than or equal to 10. So in this case, what is the value in binary? 1010. What is this? Here is a number which is more than 9, which can be represented in BCD, right? So here the result of the operation is more than 9 there. So you have to bring it to a familiar BCD form. What you have to do, whenever the result is more than 9, just add binary 6 to it to get the answer in the BCD form. So what is binary 6? 0, 1, 1, 0. Just add 6 to it. So what is the result of the operation you get here? So I'm adding 6 to it. So this will be 0 here. This will be 0, carry 1. So this will be 0, carry 1. So this will be carry 1. Now, even if there is a carry also, this is also not in familiar BCD form. So what you have to do? Add 6 to this also once again. So add 6 to this in binary. So what is happening here? This becomes 0, carry 1. This becomes 1, carry 1. This becomes 1, carry 1. This becomes 0, carry 1. Agree? Now this becomes 1, this becomes 1, this becomes 1, this becomes 0. Now, if you read in BCD, what is the value you get here? This is 7 here, this is 6, this is 0. So, is my answer now in familiar BCD form? Okay. So, this is how you do BCD arithmetic. Okay, this is how you do BCD. You should know these fundamentals. That's why I'm discussing this, right? So, whenever the result of an operation is not in familiar BCD form, what you do is, depending on the result of the operation, if at all the result of the operation is more than 9, just add 6 to it, so that you get the result in familiar BCD form. So, the concept is clear. Now, once you understand this, going further, we have understood the binary codes. They are actually classified into principally 2 categories here. What we are referring to as weighted binary codes, Then the other one is what are referred to as non-weighted codes. So examples for weighted binary codes will be 8421, 2421, 84 minus 2 minus 1. These are all examples for weighted binary codes. And examples for non-weighted binary codes can be your gray code is an example for non-weighted binary code. Your XS3 code is an example for non-weighted code. So let us understand what is a term called weighted binary code. What is this term called non-weighted binary code? Okay. Now, say for example, I want to represent 1. How am I doing that in binary? How I do in binary? 0, 0, 0, 1. So here, how am I saying that this is the binary representation of 1? Why? Because I'm assigning for every digit a value here, a weight here. So in this case, what is the weight I am assigning here? Whenever there is a 1 here, so this is given a weight as 1. So this is given a weight as 2. This is given a weight as 4. This is given a weight as 8. Okay. Now, how do you compute the value of this number? So 1 is multiplied with the weight there. 1 into 1 is 1. So this is the value 1 representing what code here. This is the weight of the representation. So in this case, it is called as 8421. Now say for example, I want to represent 2. So where should I place a 1 in this representation? I should place a 1 in the second digit, right? Then I'll get the value as 2. Right? Remaining digits I'll place a 0. So this is called as 8421 code. Now say for example, I want to represent 6. What should I do? I should put ones in such a way that the sum of the weights will give you a value 6. Sum of the weights will give you a value 6. So where can I place ones there to get value 6? I should place a 1 here. I should place a 1 here. Remaining places I put a 0. So I'll get, if you add the corresponding weights, 4 plus 2 will give you the value as 6. So this is called as weighted code. Why? Because every digit is weighted by a factor. In this case, this digit is weighted by a factor 1. This digit is weighted by a factor 2. This digit is weighted by a factor 4. This digit is weighted by a factor 8. Now say for example, I want to represent 10. How can you do that? I should place ones in this binary, in this combination, in this pattern here, so that the sum of the weights should give you a value 10. So where can I place ones for getting 10? 1, 0, 1, 0. Right? So this is called as 8421 code, which is called as weighted binary. Now you understand the term weighted binary code? Yes? Is the concept clear? Now, the same one I can represent in 84 minus 2 minus 1 also. The same one I can represent using this code as well. Now, how do you represent 1? Anybody? Any guesses there? How to represent 1 in this system? In this binary code? How do you represent 1? So, in this case, the weight is minus 2. The weight is minus 1 here. So, to get 1, what should be the binary combination I should write here? Am I getting sum as 1? 8, 4, 4 minus 2, 2, 2 minus 1, 1. This is the value I got. Now I want to represent 2. How do you do that? I want to represent 2. How do you do that? So what can be the code here? I want to represent 2. 0, 1, 1, 0. So this is the 84 minus 2 minus 1 code for 2. Similarly, I want to represent 6. How can you do that? 1, 0, 1, 0. Agree? So this is 84 minus 2 minus 1 code of representation, which is once again a binary code. This is a binary code, right? So 8421 code is a binary code. 84 minus 2 minus 1 code is also a binary code. So all my weighted codes are binary codes once again. So I can represent numbers using this code as well. But normal practice is which code is most frequently used? 8421 code is most frequently used. That is a normal practice which we follow. Are you following the discussion? Now come back to XS3. What is XS3 code? XS3 code means whatever binary code you have, to that you add 3 to it. That becomes the XS3. Say for example, I want to represent 1 in XS3. So I am here illustrating how to write XS3 code. So I want to represent 1. I want to represent 1 in XS3. How do you do that? Let us try to understand. So 1 in binary, how do you write? 0, 0, 0, 1. To this, what you do? XS3. XS3 means add 3 to it. So 1 becomes, when you add 3 to it, 1 becomes what? 4. So represent this 4 in binary. 0, 1, 0, 0. So this is the representation of 1 in XS3. This is the representation of 1 in XS3. Now say for example, I want to represent 2 in XS3. So what will be the binary code for 2 in XS3? 2 plus add 3 to it. 2 plus 3, 5. So represent 5 here. 0, 1, 0, 1. So this is 0, 1, 0, 1. Sorry. So this is the representation of 2 in XS3. 0, 1, 0, 1. So like that, I can define various codes as well. So I have illustrated some of them. So I have illustrated what is a weighted code and what is a non-weighted code. So here, are there any weights here? Are there any weights for each digit here? So that's why these are examples for non-weighted codes. That's why this is the reason why these are examples for non-weighted codes. So your XS3 code is an example for a non-weighted binary code. Your gray code is an example for a non-weighted binary code. Am I clear? Now you know how to represent any number in XS3? Yes or no? So I want to represent 12. What will be the code for it? I want to represent 12. What will be the XS3 code for 12? Anybody? 12 I want to represent it by XS3. 12 in XS3 will be what? 12 in XS3. 12 means you add 3 to it. 15. 15, how do you represent in XS3? Huh? All ones. All ones, right? 4 ones. 4 ones will be the representation of 12 in XS3. Do you agree or not? 12, if you 4 ones will form the XS3 code of 12. Agree? Not agree? 12 plus 3 is 15, right? So how do you represent 15 in binary? 8421 code, 8412, 12 plus 2, 14, 14 plus 1, 15. Put all ones in these places. That becomes 15. Agree or not? So whenever you want to represent 12 in XS3 code, you should use the binary code as 4 ones. That is XS3 representation of 12. Am I clear, guys? Any doubts here? Now, so there is one more code here which is called as gray code. So whenever you are dealing with numbers, usually most of the systems, the signal, when I say number is nothing but a voltage signal for us. So these signals, they take continuous values. Okay, they'll not take discrete values, they'll take continuous values. So whenever you want to represent continuous values, the best form of code, whenever you want to represent continuous values, the best form of code which you can use for representation is gray code. So how do you get this gray code? So take the case of a 4-bit gray code. I want to represent a 4-bit gray code. Okay. So what I do is I'll start from the least significant bit. I'll start from the least significant bit column. So this will be the rightmost place is the least significant bit column, right? So here I start with 0. Then what I do, I'll put 1 there and I'll take a mirror image of that. If you put a mirror here, what you will see in the mirror? I'll write 0, 1, put a mirror there. What you will see in the mirror? I'll say 1, 0, right? So I'll put 1, 0 there. So I am writing a 4-bit gray code. 4 bits, if I want to use, how many combinations you can get? 4 bits I am using to represent numbers. How many combinations you can get in binary? 2 power 4, right? Using 4 bits, you can get 2 power 4 combination. 2 power 4 is how much? 16. So if you want to write a 4-bit gray code, I am illustrating you how to write the 4-bit gray code. Okay. So first you start with the least significant column. You start with 0 followed by 1. Take the mirror image of that. So you'll get 1, 0. Take the mirror image of that. What will be that? 0, 1. Take the mirror image of that. What will be that? 1, 0 once again. Take the mirror image of this. It will be once again 0, 1. How many values you got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Still 6 more values. Okay. Now take the mirror image of this 1, 0. Take the mirror image of 0, 1, 1, 0. 6. Okay. Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. So this is my least significant bit column. This is my least significant bit column. Do you agree? Now go to the next most significant bit position. So after this bit, let us go to this bit. I'm writing a 4-bit gray code. I got on the least significant bit. I have to get 3 more bits to the left. Right? Now I'll start here. I started with 0 followed by 1. Now I start with 2 zeros followed by 2 ones. Then take the mirror image of this. So what will be that? 2 ones followed by 2 zeros. Do you agree? Now once again take the mirror image of that. What will be that? 2 zeros followed by 2 ones. Once again mirror image of that. 1, 1 followed by 0, 0. This will be the next significant bit column. Then once again, next column, how do you get? Now we have taken 2 zeros, right? Now you take in powers of 2. 2 power 0 is 1. 2 power 1 is 2 zeros. Now 2 power 1 is 2 zeros. 2 power 2, right? After 2, here 2 power 0 is 1 0. Next 2 power 1, 2 zeros I started with. Next 2 power 2. 2 power 2 is how many zeros I should start with? 4 zeros. So I'll put 4 zeros first. Followed by 4 ones. Now take the mirror image of that. So that will be 4 ones followed by 4 zeros. Right? The next what I'll do, next bit, 2 power 3. 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros followed by 8 ones. Now, so this is the 4-bit gray code. Using 4 bits, how many numbers you can represent? You can represent 16 numbers. So this is the gray code for number 0. This is the gray code for number 1. This is the gray code for number 2. This is the gray code for number 3. This is the gray code for number 4. This is the gray code for number 5. This is the gray code for number 6. Gray code for 7. Gray code for 8. Gray code for 9. Gray code for 10. This is the gray code for 11. This is the gray code for 12. This is the gray code for 13. This is the gray code for 14. And finally, this is the gray code for number 15. So in this way, I can represent the first 16 numbers starting from 0 in gray code. This is the gray code. Am I clear? So you should know all the representations. You should know how to represent a number in 8421 code. You should know how to represent the number in, say, I give you 2421 code. You should be able to do that. I should give you, I'll ask you to represent number 15 in gray code. You should tell me this binary combination, 1 followed by 3 zeros. You should know all these things. Whenever we go into the design, we'll be using these concepts. Okay. So now you understood how to write the gray code of a particular number. Yes. So I will illustrate it for the case of 4-bit gray code. Similarly, you can repeat it for even 5-bit also. 5-bit, how many combinations you get? 2 power 5, 32. So that means you can represent 32 numbers using 5-bit gray code. Starting from 0 to, what is the last number you can represent using 5 bits? 0 to 31. 32 numbers, right? 0 to 31 you can represent using a 5-bit gray code. You can easily generate now. You know the logic, right? You can easily generate the gray code. Right? These things are required. So how to represent a number using gray code? How to represent a number using 8421 code? How to represent a number using BCD? How to represent a number using 2421 code? All these things are required. Now you know what is the difference between a weighted code and a non-weighted code. Here, is there any weight associated with the digit there? No. So gray code is an example for a non-weighted binary code. XS3 code is an example for a non-weighted binary code. Am I clear, guys? Now. So there is one more specialty here. The specialty is so 2421 and 2421 code and XS3 codes are examples for self-complementing codes. So please understand this term called self-complementing. So what do you mean by self-complementing? So self-complementing codes have the property that 9th complement of the decimal number can be obtained by directly interchanging ones and zeros. So please understand here, when you say a code is self-complementing. So a code is said to be self-complementing if it has the property that 9th complement of the decimal number can be obtained directly by changing ones with zeros and zeros with ones. If at all the system, the number has that property, then you say it is a self-complementing code. So 2421 and XS3 codes are examples for self-complementing code. So as an example, 395 if you represent in XS3, this will be the value. 395 is XS3. So 3 means 395 is how you represent in XS3. Now what is the specialty here? Take the complement of this. This becomes 1110 here. I'm taking the complement there. So I'm replacing zeros with ones and ones with zeros. That is how you get the complement, right? So when you take the ones complement of this number, which is represented in XS3, what you get? I get 604 in XS3. So which is that? What is 604? 604 is nothing but the 9th complement of 395. You know how to compute the 9th complement, right? How to compute the 9th complement of a decimal number? Subtract the given number from those many digits of 9. Subtract the 395 from 999. What do you get? 604. So this is the this is XS3 code for 604, which is the 9th complement of 395. So this is the property of this XS3 system. So that is why 2421 code and XS3 codes are examples for self-complementing codes. You can get the 9th complement of the decimal number by just replacing zeros with ones and ones with zeros. That is the special property exhibited by these two codes, XS3 code and 2421. That's why they are referred to as self-complementing codes. Am I clear, guys? Now, so after understanding the binary codes and the various different forms of binary codes there, let us go further and try to understand some more important things there. Now we have a small theory coming up. Now we'll try to introduce this concept of Boolean algebra. So binary logic. So let us understand this term called binary logic. So when I say binary logic, it consists of binary variables. So when I say binary logic, it consists of binary variables, and what are the operations involving binary variables? So what are the operations involved there? There are logical operations involved. So binary logic consists of binary variables and their associated logical operations. So these variables can be represented using any of the letters of the alphabets. I can represent the binary variables as capital A, capital P, capital C, or using small case letters as well as X, Y, Z. Okay. So this is a binary variable form. So what do you mean by a binary variable? So any variable which can take only two values is called as binary variable. And what are the two values it can take? It can take either value 0 or it can take a value 1. So whenever this variable A here takes a value, whenever this variable here A takes A can take only value, A can be either 1 or 0 or 0. So then in that case I can consider this as a binary variable. I can consider A as a binary variable. Okay, similarly, if at all I represent a binary variable as X there, so this X can take only two values. It can take either a value 0 or a value 1. So therefore, I can consider this X as a binary variable. And whenever you are talking about the operations involved on that, we call that logic as binary logic. Okay, now let us proceed further and try to understand some more details there. So here, all of you know these things, but just a repetition of things which you already know. So Boolean algebra. So our entire subject of digital system design is based on this concept of Boolean algebra. So Boolean algebra, as any field of algebra, any mathematics of any algebra satisfies certain properties. So any system which you define, it satisfies certain properties, and all of you know these properties. It has to satisfy closure property, it has to satisfy associative property, commutative property, it has to have an identity element, it has to have an inverse element. All these things you already know, right? So any system which you define, any algebra which you want to define, it has to satisfy these set of properties. Okay, so it has to satisfy closure property, it has to satisfy associative property, commutative property, it has to have an identity element, it has to have an inverse element. Like that, in the case of a Boolean algebra also, we define variables such a way that these variables satisfy these set of properties. Now, all of you know what is closure property. So I define a closure property in this way. A set S is said to be closed with respect to binary operator if for every pair of elements of S, the binary operator specifies a rules for obtaining a unique element of S. Just a minute, madam. అదే నేను మేడంతో చెప్పాను మేడం కొన్ని అంటే ల్యాబ్ ఉంది, ల్యాబ్ క్లాస్ ఉంది, నేను ఫస్ట్ పర్సన్ మార్నింగ్ చెప్పాను. చూస్తాను మేడం, చెప్పాను మేడంకి అయితే ఇన్ఫార్మ్ చేశాను నేను. అన్నారు కానీ అదే మార్నింగ్ అయితే చెప్పాను మేడం, వీలవుతే వస్తాను, టువర్డ్స్ ద ఎండ్ అన్నా వస్తాను, క్లాస్ అయిపోయింది. ఫస్ట్ రావడం కష్టం ఎందుకంటే ల్యాబ్లో నేను ఫస్ట్ పర్సన్. Okay, Now, any set S is said to be closed with respect to a binary operator if for every element, every pair of elements belonging to S, the operator specifies a rule for obtaining a unique element. Let's take an example for a set of natural numbers. So, how do you define the? So, what is happening here? Whenever the system has to satisfy this closure properties, take any two numbers from the set here. Say, for example, I consider 1 and 2 here, and I define an operator as plus here. So, I add these two numbers. What happens? 1 plus 2 will give you the value as 3. 3 is once again belonging to the set. So that means I can say that the set of natural numbers is closure with respect to the operator plus, which is addition. Agree? So the closure property is satisfied with by the set of natural numbers for the operation called addition. Am I clear? Now, say for example, I take once again two numbers from this. So I'll take 1 and 2. Now I consider the operator as minus. So what is 1 minus 2? What is 1 minus 2? It is minus 1. So is minus 1 belonging to this set? No. So therefore what you say here? The set of natural numbers is not closed with respect to what operator? With respect to minus operator. So you are defining the closure property with respect to the operator which you are defining. So in this case, the set of natural numbers is satisfying the closure property with respect to addition operation, whereas it is not satisfying the closure property with respect to minus operation. Am I clear there? So that is your closure property. Similarly, when you say this is the associative property. So if I define a binary operator asterisk on a set S such that this equation is satisfied, okay, then we say that the system is satisfying the associative property. Okay, all of you know these things, right? Now, similarly, I have a commutative property. It says that if I define an operator like this, star on a set S, then it is satisfied the commutative property if it satisfies this equation. X asterisk y should be equal to y asterisk x there. So whenever this equation is satisfied, I can say that the commutative property is satisfied. Similarly, I can define the identity element of a set. Okay, so a set is said to have an identity element with respect to the binary operator asterisk on S. If there exists an element E belongs to S with the property E asterisk X should be equal to X asterisk E, where asterisk is the operator there, which is equal to the same number X there. Okay, so in this case, the element 0 is the identity element with respect to the addition operation on the set of integers. Okay, as an example for this. So x plus 0 is always equal to 0 plus x, which is always equal to x there. Therefore, I can say that 0 can be treated as an identity element with respect to the addition operation for the set of integers. Okay. Similarly, you can define your inverse element. Like that, whenever you want to define a particular set or a particular algebra, algebra is the foundation of the number system, right? So whenever you want to define a particular number system or particular algebra there, that particular algebra has to satisfy these set of properties. Similarly, in our discussion, Boolean algebra, which we are going to introduce now, it also satisfies these set of properties. Okay, so Boolean algebra is also one branch of mathematics which satisfies this set of properties there. Okay, satisfy this set of properties. So let us try to understand the details about that. So I'm not going into details of this. So all these properties have to be satisfied. So an example of an algebraic structure is a field there. So what is a field? A field is a set of elements together with two binary operators, each having the property 1 to 5, which I have listed now. So whatever operators which we have defined, if all these properties are satisfied by a set of elements together with some binary operation there, then I consider it to be as a field there. Okay. Now the set of real numbers together with the binary operators plus and dot, they refer to the field of real numbers. Similarly, the field of real numbers is the basis for arithmetic and ordinary algebra there. Okay. So this is some mathematics there. Now let us go into the actual discussion. So how do you define this concept of Boolean algebra? So Boolean algebra was actually introduced by the scientist called George Boole in the year 1854. And in the later year, 1938, C.E. Shannon actually introduced this concept of two-valued Boolean algebra. This is very important for us, two-valued Boolean algebra, which is also referred to as switching algebra, in which he demonstrated the property of a bistable electrical switching circuits, which can be represented by this algebra. So using this concept of Boolean algebra, we are going to make our entire discussion. And this Boolean algebra is forming an algebraic structure which is defined on a set of elements B together with two binary operators. So what are the two binary operators which we define here? We define two binary operators. One is represented as plus and the other one is represented as dot here. And what are my elements here? I'm talking about Boolean algebra or binary algebra here. So when my set consists of only two numbers, the numbers can be either 0 or 1. The set consists of only two elements. The set consists of only two elements, either 0 or 1. And what are the operations I am defining? I am defining only two operators here. One is represented as plus, the other one is represented as dot here. So what is plus, what is dot? We'll try to understand now. So this Boolean algebra is satisfying the closure property with respect to plus operator. It is satisfying the closure property with respect to dot operator. So it is satisfying, it is having an identity element. So in this case, the identity element with respect to plus operator is 0 and identity element with respect to dot operator is 1 there. Okay, and it is satisfying the commutative property with respect to plus operator. It is satisfying the commutative property with respect to dot operator, and it is distributive over addition. Dot is distributive over addition, and similarly addition is distributive over dot. So all these properties are satisfied. All the 6 properties of closure, associative, commutative, identity element, inverse element, all these are existing for the case of Boolean algebra, where the set consists of only two elements, 0 and 1, and the operators which are defined are plus and dot. So how do you actually define these operators? Let us try to understand that. So in our case, the plus operator represents logical OR operation. The plus operator represents logical OR operation, and the dot operator represents logical AND operation. Okay, now let us come to the actual discussion of a two-valued Boolean algebra. So let us understand two-valued Boolean algebra. So in this case, my set consists of only two elements, 0 and 1. And what are the operators involved there? The operators which are involved there are plus and dot. So here I am defining what is plus now. So plus is referred to as logical OR operation. Logical OR operation, and dot is referred to as logical AND operation in the case of two-valued Boolean algebra. Logical AND operation. Now, let us understand what happens when you consider two variables x and y. So these are my two variables where I am operating. So when I say two variables, these are two variables x and y here. X can take either value 0 or 1. Y can also take either value 0 or 1. So every element, every variable here can take one of these elements. Okay. So two variables, how many possible binary combinations can I have? X can take 0. Y can also take 0. This is one possibility. What is the other possibility? X can take 0. Y can take 1. What is the other possibility you have? X can take 1. Y 0. X can take 1. Y can take 0. So these are the four possibilities of the two binary variables x and y. So two binary variables, how many possible combinations you can have? Two binary variables, how many possible combinations you can have? 2 power 2, that is equals to 4. These are the four binary combinations. Now I operate between these two variables. I say x logically odd with y. So what will be x logically odd with y? 0. This will be 0 odd with 1, that will be 1. 1 odd with 0, 1. 1 odd with, this will be 1 here. So 1 odd with 1 will be 1. So this is how you do this. You define this first operator, which is called as logical OR operator in the case of a two-valued Boolean algebra. Am I clear there? Now, similarly, let us try to define the operator called AND here based on the case of two variables. So in this case, once again, two variables, four combinations, 0, 0, 0, 1, 1, 0, 1, 1. Now, if I do an operation called AND between these two variables, what can be the value here? 0 and with 0, 0, 0, 0, 1. So this is the first operator which we can define on the case of two-valued Boolean variables there, x and y. This is the second operator which we can define there. So this is logical OR, this is logical AND. Now in addition to this, I can also define one more operator which is referred to as NOT operator. I can define one more operator which is called as NOT operator. So usually you represent this as a complement. So say for example, if x is my binary variable, I can define the not operator on X as either X bar or X complement like this. Okay, so I can define a not operator on this. So I'm here talking with respect to a single variable. So what can be the not operator for this? X can take either value 0 or 1. So in that case, what will be X bar? Can become 1 or it can be 0 like this. So this is the third operator which you can define in the case of binary variables. So how many operations which we have defined now? 3 operations which we have defined. What is logical AND, what is logical OR, then what is not operator. So once we know this 3 operators, now this Boolean algebra once again satisfies a very important property. So for every element X belongs to B, there exists X complement called the complement of X belonging to B such that X plus X bar equals to 1 and X dot X bar equals to 0 then. So that is one important property you should understand that. So for every X belongs to the set B there, where B can have only 2 elements, 0 or 1. Okay, so for every X belongs to B, I can have an element X complement which is also belonging to B such that X plus X bar equals to 1 and X dot X bar equals to 0. So the Boolean variables, they also satisfy this fundamental axiom. X plus X bar will be always equals to 1 and X ANDed with X complement will be always equals to 0. You can easily verify this. Say for example, X takes value 0. What will be X complement? 1, right? So in that case, is this property satisfied? 1 plus 0, 1. Is this property satisfied? 1 ANDed with 0. 0, right? So all my Boolean variables, all my binary variables, they satisfy these 2 fundamental axioms. X plus X complement will be always equals to 1 and X dot X complement will be always equals to 0. 0. Am I clear, guys? Now, what happens if I do this operation? What happens if I do this operation? X ANDed with X. What will be this? What will be this? X can take, say for example, X is taking a value 1. So in that case, what happens to X ANDed with X? 1 ANDed with 1. What is equals to 1? This is equal to what? Once again X. So I can write this X plus X will always be equal to X. X ANDed with X will always lead to X. Am I clear? Now, similarly, take X plus X. What will be this equal? X once again. So say for example, X is equals to 1. So 1 plus 1. 1 logically OR with 1 will be leading to 1. Take X takes a value 0 there. In that case, what will be this? 0. Logically OR with 0. What will be the value of this? 0. So can I write X plus X will also be equal to X? So these are once again fundamental axioms of this Boolean algebra. So please, you have to remember these concepts. These things you should know. X plus X bar will be always equals to 1. X dot X bar will be equals to 0. X ANDed with X will be equals to X, and X logically OR with X will also be. So this the circle things which you see here, they are the fundamental axioms. Fundamental axioms of Boolean algebra. What do you mean by an axiom? What do you mean by an axiom? Fundamental axioms of Boolean algebra. In mathematics theory, what do you mean by axiom? Axioms are statements which we are assuming without any proof. But here we are able to prove it by taking certain value. But these are statements which are assuming without any proofs there. So these are the basic fundamental axioms based on which this concept of Boolean algebra has been developed. Okay. So now you know these fundamentals now. You are able to grasp these fundamentals. Yes? Now, after understanding these fundamentals, let us proceed further. So all my properties are satisfied by the Boolean algebra there. All my properties are satisfied by the Boolean algebra. Closure is satisfied. Associative property is satisfied. Commutative properties are satisfied. There is an identity element. There is an inverse element also. Okay. All my properties are satisfied. Therefore, it forms a field for us. So using this field, I can develop my theory on it. Okay. Now, once you understand these things, let us list out the basic theorems and postulates of Boolean algebra. All of you please make a note of these fundamental postulates of Boolean algebra. The first one says x plus 0 will be always equals to x. So these are my fundamental postulates or fundamental axioms of Boolean algebra. Please, all of you should make a note of these fundamental postulates of Boolean algebra. Axioms of Boolean algebra. So first one says x plus 0 will always be equals to 0, x added with 1 will be always equals to x. Similarly, second one says x plus x bar equals to 1, x dot x bar equals to 0. Then third one says x plus x equals to x, x added with x will be equals to x, x plus 1 equals to 1, x dot 0 is equals to 0. These are my fundamental axioms of Boolean algebra. These things are very, very important. You should know these things. Then only we can understand the coming things. These are the fundamental postulates and fundamental axioms of Boolean algebra. Please, all of you make a note of these things. Then what is referred to as involution? X complement whole complement is referred to as involution. X complement whole complement is always equals to x. Then how do you write commutative in the case of Boolean algebra? X plus y will be equals to y plus x for the logical OR operation. And if you write that with respect to logical AND operation, it will be x ANDed with y will be always equals to y ANDed with x. This is called commutative property for the case of two binary variables. Similarly, associative property x plus y plus z can be written as x plus y logically OR with z. Similarly, associative with respect to AND operation, x ANDed with yz will be equals to xy ANDed with z. This is called associative property. So you please make a list of these things, fundamental postulates and axioms of Boolean algebra. This one is very, very important. Distributive x ANDed with y plus z can be always written as x ANDed with y plus x ANDed with z. And alternately, I can write x plus yz can be represented as x plus y into x plus z, where here dot means logical AND operation. Dot means logical operation. Wherever I am not putting a dot, that means there is a logical AND going on there. X plus yz. This is another form of distributive property. X plus yz can be written as x plus y into x plus z. Yes. Now, finally, an important theorem which is called as De Morgan's theorem. All of you, I think most of you will know it from your previous classes. X plus y whole complement can be always written as x complement ANDed with y complement. It's called as De Morgan's theorem. First statement of De Morgan's theorem. Similarly, xy whole complement can be written as x complement ANDed with y complement, logically ordered with y complement. So I can generalize this De Morgan's theorem for the case of n variables as well. So I can write it for the case of 3 variables as x plus y plus z whole complement can be written as. I can write for the general case as well. I can write the De Morgan's theorem for the case of 3 variables as well. How can you write that? In the case of 3 variables, my De Morgan's A statement can become x plus y plus z whole complement will be equals to x complement ANDed with y complement ANDed with z complement. Similarly, B property can be written as x, y, z whole complement can be written as x complement logically ordered with y complement logically ordered with z complement. So in this way, I can generalize it for the case of n variables as well. I can generalize it for the case of n variables as well. And finally, 10th one is called as absorption property. Absorption theorem there, x plus xy equals to x always. X plus xy is always equals to x. 10th one is called absorption theorem there. X plus xy is always equals to x, and x ANDed with x plus y is always equals to x. Okay. So these are my list of fundamental postulates and axioms there. Yes. So once you know these postulates and axioms, based on this, you can develop your theory. So let us prove some things here. So as a first one, x plus x equals to x. How do you prove that? x plus x equals to x. How do you prove this? How do you prove x plus x equals to x? How do you prove this? Fundamental axioms. You have to use fundamental axioms in order to prove it. Fundamental axioms of Boolean algebra whenever you want to prove these things. Okay. So you start from LHS. LHS is x plus x. So I can write this x plus x as x plus x, which is logically ANDed with 1. I can write something like this. I can write something like this. I can rewrite x plus x as x plus x logically ANDed with 1. You are following? Now this 1 here, I can write using the fundamental axioms as x plus x complement. Can I write like this? One of the fundamental axioms says that x plus x complement is always equals to 1. This is the fundamental axiom of Boolean. So I am replacing this 1 here using this fundamental axiom x plus x bar. Now, after writing like this, I can use the distributive property which we have just now listed out. So the distributive property says that x plus xy, x plus yz, say for example, x plus yz can be always written as x plus y into x plus z. This is the distributive property which you have seen just now. So in order to simplify further, I'll use this distributive property where in place of y, what I have here? In place of y, I have x here, and in place of z, what I have? X bar. You are following? So I am using the distributive property here so that I can rewrite this expression here. So when you rewrite this expression, I can write it as using this distributive property here. I can write it as x plus yz, where y is nothing but your x and z is nothing but x complement. X plus x into x complement. But what is this from the fundamental axioms? X complement is always equals to 0. So this becomes x plus 0. And what is x plus 0? X. X logically odd with 0 will be equal to x. So this is how you can prove this statement here using the fundamental axioms. So where I have repeatedly made use of the fundamental axioms and the distributive property which you have just now listed. So you should be able to apply these fundamental axioms and theorems which you have made you just now list out in order to prove these statements. So this is an illustration for that. How do you apply the fundamental axioms and theorems in order to prove some statements here? So is the proof clear to you? So in this way, we'll be using this kind of application where I'll try to use the fundamental axioms and theorems in order to simplify Boolean expressions. So let us understand this term called Boolean expressions. So any algebraic expression which involves binary variables is called a Boolean expression for us. Any algebraic expression which involves binary variables is a Boolean expression for us. So I can have an expression like xy plus yz plus zx. This is a Boolean expression for it, where every variable here is a binary variable. It can take only, x can take only 0 or 1. Similarly, y can also take 0 or 1. Okay, z can take a value 0 or 1. So I'll be regularly using in our discussions in the coming classes. I'll be regularly using the list of fundamental axioms and theorems which you have just listed down in order to simplify the Boolean expressions. So how do you actually do that? We'll try to understand in the coming classes. For now, what you guys do is I just share this PDF on the Teams there. Please go through this PDF for this list of fundamental axioms and theorems there. And in the coming classes, we are going to use them again and again for our discussions. Okay. So online guys, did you follow the discussion of today? Online guys, anybody?
Yes, sir.
Okay. So let us go further from here.